All righty. Wow, there is an echo. And we're up. Well, thank you for joining me this morning. We're going to basically cover everything in the next 30 minutes. So all the basics of MRI plus some of the newer tricks that we're starting to apply to the and fMRI acquisition. Before I start, I'm compelled to disclose that I have some research support from Siemens Healthcare, and that everything I discuss will be non-FDA approved devices. So let me just step back before I start and ask why we're trying to improve fMRI methods. We're all sort of aware of the length scales of the central nervous system, from the sort of 1 meter spinal column to the lobes of the brain to, say, the Brodmann areas. And these are traditionally the length scales that fMRI has operated on, sort of Brodmann area sized activation patches. But of course, as you drill down, you get more. First of all, the cortex itself is only, say, 2 to 3 millimeters thick. And so a conventional 3 millimeter fMRI voxel doesn't actually even resolve the cortex. You need 2 voxels across something to resolve it by the Nyquist criteria, and 2 3 millimeter voxels doesn't cut it. So the cortex is where the action is, and we can't even resolve it. So there's something we want to fix right there. But even within the cortex, of course, there's 6 layers, and function tends to follow these structures and columns. And of course, you drill down even more, you see the cellular level and the synaptic level. Probably not going to get to those right away, but we would like to get to these laminar and columnar levels. So this is really what's in our target, what our target is for improving fMRI methods. And it's really not so bad. We've made a lot of progress. I mean, on the left, I pulled up an old 3 millimeter fMRI that I took back from the early 2000s off one of our 3T scanners. And on the right, I have basically the best single shot EPI functional run that we can currently acquire at 7T. It's about 0.75 millimeters isotropic. And you can immediately appreciate that one is actually resolving the cortex. This is a T2 star weighted image from a functional run, and you can see anatomical detail. It's actually higher resolution than a conventional anatomic image that we would take. And so, of course, we also need to get the whole brain. At this 0.75 slices, you have 120, 130 slices to cover the brain. And if you do that with a TR of 4 seconds, that's going to take forever. And so we need to get that down into a reasonable amount of time. I'm sorry, if you do that at a rate of, say, 15 slices per second, that will take a TR of something like 10 seconds, and that's too long. It also needs to be accurate. It's not good enough to just have super high resolution. Ultimately, we want to paint activation onto the folded cortex, and even as a function of laminar depth in the folded cortex. And that means that whatever method we're taking these anatomical surface contours from, the fMRI needs to match it to within maybe 1/10 of a millimeter. And that's what starts to get really hard with EPI. And we can show that we can do very good cortical surface definitions, and going to a little higher MP range, say here showing a 0.4 millimeter isotropic MP range, you can really see the accuracy of the surfaces is quite good. But what happens when you superimpose an EPI image on it is problematic because of the subtle distortions, or not so subtle distortions in the EPI. So one of the things that we found really helps is simply moving to an all EPI exam. So here we have structure function matched images. So the distortions are present in both, and yes, they're both distorted a little bit because they both derive from EPI images, but we're using a similarly distorted image to define these laminar contours, and then we know we'll be in agreement with the fMRI data, which was taken with the same exact EPI readout. So the way we do that is we take this high-res EPI readout, and we just put an inversion recovery, and we do a bunch of different inversion times, and we generate a T1 map. Then we take that T1 map, and we actually generate a T1 weighted image that is suitable for FreeSurfer. Probably it would be best to just modify the surface contour method to fit a T1 map, but this is a way to sort of shoehorn it in. And you can see you can run an EPI set of images through FreeSurfer and get pretty good surfaces. And the important thing is that now the structural image matches the functional data, the match distortions. So everything is a little distorted, but it'll be in correspondence. And we've taken this one step further. You can, of course, do T2 with a spin echo with the same EPI readout. You can add some diffusion gradients, and you can do diffusion with the same EPI readout. Everything has the same EPI readout, and therefore match distortion to your functional imaging. And in the brainstem, for instance, this is work of Marta Bianacardi. She's found it very useful to have the diffusion imaging. Finding your way around the brainstem is difficult, even if you're a pretty knowledgeable neuroanatomist, and it's just very helpful to have as many different image modalities to guide you around. So T2, T2 star, and diffusion really help along with the T1s. And I mentioned getting the number of slices up, and that's been a key development in the last 5 or 6 years, and that is a simultaneous multi-slice acquisition method, which was actually introduced in 2001, almost 2 decades ago at this point. And that's simply taking multiple slices. Here's 3 slices. You take them simultaneously, and then of course when you march through the brain, you get everything 3 times faster. And of course, the 3 slices are pancaked on top of one another. They're aliased. And we know all about how to unalias things, the sense method. There's also grappa methods to unalias this sort of thing. But the alias pixels are quite close together in space. In this case, they're about 3 centimeters apart in the z direction. That's a challenging sense, applying the sense method to that is challenging. Typically, the sense R equals 2 image would be aliased by half the field of view, so more like 10 or 12 centimeters. So what Count Setzenpop did was he showed how to slice shift every other slice so that now the alias pixels are half a field of view apart in Y plus the 3 centimeters in Z. So now it's actually an easier problem than the rate 2 sense. And when we pull them apart, we get the 3 images with almost no penalty, no G-factor penalty. First of all, there's no square root of R penalty like we normally see in sense, but we're not leaving out data in this aliasing problem. We're not skipping lines in K-space. We have the signal from all of those spins. So there's no square root of R penalty, and that's an amazing big benefit. But there's also very little G-factor penalty because it's a relatively easy unaliasing if you're only doing, say, 3 slices. So the net effect is 3 slices we get virtually for free. That's 3 times as efficient. You're just covering the brain more efficiently. It drops right to the bottom line. Here's an extreme case of 12 slices done simultaneously with a 64-channel coil at 3T, and it shows that we can really remove the speed barrier here. The whole brain covered in 350 milliseconds, about 1/3 of a second. So 170 slices per second are reconstructed on the scanner. The reconstruction lags a little bit. But why improve temporal resolution? You know, in the events that we're trying to see, there's of course action potentials at about 1 millisecond. The postsynaptic dendritic currents are about 10 times longer. And of course, the hemodynamic response is even longer still at 5 or 6 seconds. And that means that the hemodynamic response, of course, adds most coherently of all. And that's a good thing for seeing it. It means, though, why would you need a resolution faster than 6 seconds? Here's a power spectrum of a typical fMRI run. You see the little cardiac bump. You can actually see on the far right a little bump at 2 times the cardiac frequency. You see the respiration bump, and you see the area where the bold is. And I just point out that it's a logarithmic scale. So really, I mean, getting fast enough to get rid of the cardiac and respiration bumps by filtering them out, Nyquist sampling and filtering them, is a good thing, but their power is pretty far down. I would argue that actually the real benefit of going too fast comes from an efficiency point of view. And you might ask why. We all know from the sampling theorem that oversampling a waveform and then filtering it down to the bandwidth of interest is equivalent to simply Nyquist sampling at the bandwidth of interest. There's no win from oversampling like that in a signal-to-noise point of view. It's a slight win in digital resolution. But so if those two are equal, why do we want to go faster? And I think one way to look at it is that Nyquist sampling theorem doesn't quite hold for us because we have gaps between our samples. If this is the dwell time of your sampling, what Nyquist is really talking about is a sampling that looks more like this, where there's no gaps. In other words, the ADC actually connects a capacitor, a sample and hold, to the voltage and integrates for the entire dwell time. Well, we don't do that in EPI. When we take 10 slices a second, that means that we're sampling the signal in a 2-second TR. We're sampling for about 30 milliseconds, the EPI readout. And so we're sampling for only 1.5% of the time. So my suggestion is that sampling faster probably helps just make that more efficient. So what's holding us back? There's other things, of course, susceptibility effects. Of course, the microscopic susceptibility is good. That's what gives us a bold signal. The macroscopic, from, say, the air in the frontal sinuses, is bad. That gives us this big signal dropout that we all have seen in the orbital frontal cortex. And, of course, it gives us the ugly distortions in EPI. And I'll talk about each of these separately, but I'm just going to get everybody on the same page and just quickly go through my version of the physics of MRI. We're all looking at water. The proton in the hydrogen atom has a basic nuclear spin. It has both angular momentum and magnetism. So we draw it something like this. You can think of it as a spinning ball of charge. A spinning ball of charge, of course, is a little circular current. That gives rise to the magnetic moment like a compass needle. And then we get that processing, and we generate a deflux dt in our coil and get our voltage. We encode it with gradients to get k-space and then form our image. So these magnetic dipoles, you can think of them as little spinning charged balls. You can think of them as a little current loop. You can think of them as a little bar magnet. Doesn't matter. We will sum them all up, and all the net alignment we'll call big vector M. And so this net alignment isn't as strong as you think because there's a lot of thermal agitation, and only about 1 part in 10 to the 4th are aligned, even at 7T. So these little bar magnets, of course, align with a big static magnetic field, just like a compass needle aligns in the Earth's field, but they also possess angular momentum. So that means when you pull them away from north, they don't just simply go back, they'll precess around north like a top. A top has angular momentum and gravity pulling it down. You can think of the spin as having angular momentum and this magnetic restoring force trying to pull it back to equilibrium. The equations of motion are exactly the same. It's the equations of motion of a gyroscope. And it's this fundamental precession frequency which we're going to detect. And this is the only equation anyone ever needs to remember in MRI, that the frequency of the precessions proportional to the field with a fundamental physical constant. Once we get it precessing, then we can see it, because the flux from all this magnetization will thread through a loop of wire, our RF coil, and that flux integral is oscillating at cosine omega t. Of course, by Faraday's law, there'll be a voltage induced. This is how a generator works. Deflux dt, generating electricity. The derivative pulls the omega out front, so the voltage goes up with higher frequency. So that's one reason why bigger magnets are better for us. So we detect this voltage, and so you can think of the two components that are important to us. The Z component, that kind of tells us how much magnetization is stored and ready to go for the next shot. And then there's an XY component. That's the processing part. That's the stuff that's moving. That's what we're going to detect and use to encode a signal and create an image. So that's the really important one, but we keep track of both because we also need to know how much is left in the bank for the next shot. And then we do our image encoding with a gradient. A gradient is a very simple additional field that we put on that looks like the middle diagram. It's just simply linearly changing, say, across the X dimension, left to right. Added to the trim field, the fields just add. You just get a little trim field on top of that big static field. I haven't drawn it to scale. It's really more at the 1% level. So frequency encoding is the easy part to understand. You turn on the gradient, you take your signal, And thanks to that magic equation, frequency is proportional to field. Before the gradient, everything's processing at one frequency. After the gradient, things process at different frequencies, say the left ear at the lowest frequency, the right ear at the highest frequency. The amount of signal is simply the integral of water across the head or object at that position. So what we end up with is a projection image. And actually, this was well understood in 1950. And so one of your homework questions is to try to figure out why did it take an additional 35 years to develop MRI. Okay, so the pulse sequence looks like this. RF excitation with a slice select. We turn on our readout gradient. We collect our points. We get that 1D projection image. And here's one reason things go wrong. If we have an inhomogeneous field like that frontal sinus bubble, you can see it either adds to or subtracts from this gradient, and it distorts that 1D projection image, but just in that location where there's a problem. So here's a ping pong ball taken with different readout gradient strengths, so different bandwidths, and you can see that only the highest bandwidth, where the applied gradient is strong compared to these local gradients, do we get a nice round ping pong ball. Now the hard part to reconcile in your cocktail party conversations about MRI is the phase encoding. And that's this little blip that we're going to use to encode the Y direction. But I'll show you it's really the same as frequency encoding. They can be understood at least on the same level. So now if we look at the frequency, you get a distribution of frequency in Y while this blip is on. But before the blip, all the Y locations are processing at the same frequency. And after the blip, they're all processing at the same frequency. So reading out the signal after the blip, the frequency is not going to tell you anything about Y because all the locations are processing at the same frequency. But phase is frequency times time, and now we see that there's a phase shift that's dependent on Y position. And I've put a parentheses around the gamma, G, and the T, the length of the blip, and renamed it with a mysterious constant called K, just to show that phase is proportional to position with that constant K. And that is, of course, the infamous K-space location, but we'll get into that in a second. So we give a 90-degree pulse, we turn on the blip, stuff at the forehead gets ahead in phase, stuff in the isocenter is our reference zero position, stuff in the bottom of the head drops behind in phase, and importantly, this phase relationship is locked in once the blip is over. Everything goes back to the same frequency, so there's no relative motion of these vectors. So if you look at that from a continuous point of view, what you've done is wound a helix in phase in the Y direction, and once a blip is over, this phase helix is locked in. And this is critical for tying it into the K-space picture. If you have a small blip, you wind a very loose helix. A medium blip, it goes a little tighter, and a large blip, very tight. And by large, it's either the gradient amplitude or the duration of the blip. It's really just the product of those two that matter in that definition up above, or equation up above. So the key insight is from looking at what an actual object produces when you do this. If I put in my biggest uniform phantom and I put on a little blip, I get nothing. All of the signal, for every vector pointing to the left, there's one pointing to the right, and there's complete cancellation over multiple cycles of that helix. My biggest object gives no signal. However, if I put in a periodic object, like these little test tubes, where I happen to pick the spacing to exactly equal the periodicity of the helix, then I see every bit as big a signal as if I hadn't blipped on the gradient at all. The gradient sort of lets this signal pass through. It picks out the part of the object that happens to be periodic at that periodicity set by the helix you created, which is set by that gradient moment of G times the length of the pulse, tau. So what we simply do is blip on a gradient, record the signal, and that tells us how much a signal is coming at that spatial period. So it's a spatial periodicity, or 1 over period is frequency, so you can call it a spatial frequency. It's confusing because we've been talking about frequency, temporal frequencies of precession. This is a spatial frequency. A sine wave is a function of space. So you kind of have to sort that out in your mind. So the amplitude tells us how much of the object is modulated in at that frequency. The phase tells us something about where it's slid relative to that helix. You can think about that a little bit. And anyway, all we have to do is collect all these phase-encoded points, and then we have a Fourier representation of the image, and we can take the Fourier transform and get the image. The way I described it, I sort of blipped on a gradient, and then I sampled, and I got 3 different points this way. That's kind of inefficient. I could just leave the gradient on, then the helix is continuously winding up, and I'm sampling it at different tightnesses of the helix. That's just simply a more efficient way to do it. And if you do that, you happen to recognize that's what frequency encoding is. We leave the gradient on and we sample the points. And now I have a little GIF here showing you what the helix looks like. And notice there's a very special point at kx equals 0, which is coming up with a yellow dot right about now, which is where the helix is completely unwound. That's where we've sampled the DC, or the zero spatial frequency signal. That's where the big bucket of water phantom gives us a signal, because it's uniform across X. And your head to first order is a big bucket of water, so that's where your head gives the biggest signal. So we give it a special name, we call that the gradient echo, and we give the time that that's acquired a special name, the TE of the sequence, or time to encode or time to echo. Because if you plot the signal, it looks sort of like an echo. So our sequence would look something like this. We do the excitation, then we wind a big minus Y helix and a big minus X helix before we even acquire an image, a data point. That means our first data point is the lower left corner, and then we reverse the X gradient and read across it, filling in all the lines in the KX direction. And then we wait for T1 recovery, and we do it again and again and again. And each time with a slightly smaller little pre-blip on the Y, and we take a different line in KY, and in this way we fill up the whole KZ matrix. This is your basic garden variety flash sequence. And just a few tricks about Fourier transforms. Of course, the information content is the same in the 2 domains. If you have 256 by 256 complex points in K-space, that will be the number of points in your image. There also will be complex points. Given the resolution depends on the tightest helix that you wind. The field of view you can easily figure out depends on the spacing, since the number of points is equal. And of course, if you take higher and higher K-space, you get higher and higher resolution in the image. To see that sharp edge, you need to wind a very sharp, very tight helix. The other feature of the Fourier transform is that it assumes that the object is periodic. And because we pretended that the head is periodic, the image we'll get will be periodic. We'll get replicants of it that are periodic in the field of view. Of course, MATLAB doesn't want to fill up your entire disk drive with these, so it just saves one of them. But if you make the field of view a little too small, you will see that the other replicant will shift over on top of the one that you're interested in, and you'll get what we call image wrap. In this case, the front of the head is rolling around to the back, and you'll see the nose and the back of the head. We do this because we want to save time and image fast, and I'll get to that in a minute. So a couple more features of the Fourier transform. Even though we're always looking at magnitude images, and even when we look at K-space, we tend to look at magnitude K-space images, the phase is incredibly important. Just to demonstrate that, here's my picture. Here's a picture of Kristen, a grad student who happened to be in my lab, unfortunately present when I was putting this together a few years back. Here's my K-space, here's her K-space. All we did was take the Fourier transform of those black and white images. Of course, if you take the inverse Fourier transform, it's not very interesting, you just get the original image back. But what's interesting is what happens if I switch her phase with my phase, and now do the Fourier transform again. What do I get? Do I get myself again, in which case the magnitude information sort of dominates? Do I get her, the phase dominates, or is it some sort of just uninterpretable mess? And we won't take a vote, it takes a little too long, but the answer is it goes with the phase. So it's quite recognizable that her phase with my magnitude gives her image. And so it's just a way of saying the phase is the most important thing in this business. So with that in mind, let's look at EPI. In EPI, it starts out the same way as in Flash, where we go to the lower left-hand corner and then sample a line. But now we're not going to wait for T1. We're just going to reverse the readout and blip on a little KY gradient, which takes us up one notch, which unwinds the helix in K one notch, and then we go backwards and take the next line. And by zigzagging back and forth, whoops, we fill in the whole matrix quite quickly, all in one shot. But remember, it's the phase that matters. What happens if we get a phase error that accumulates during that time? We think of it as fast imaging. I really think we should think about it as slow imaging, because it actually takes us quite some time to traverse all of K-space. And if some phase error drifts in where each line has a progressively accumulated phase error, we'll have a problem. And that's exactly what we see. In EPI, we sort of have a fast direction. The points in the KX direction are taken quite close together in time, but the points in KY are taken quite far apart in time. That leaves time for a phase error to accumulate, say from a little local susceptibility gradient competing with applied gradients. And so physiological fluctuations also sneak in, and that's one of the reasons why we do single-shot EPI, is then they don't have time. They're limited to just that readout period and corrupting the image. So for EPI, the important metric is what we call the echo spacing. That's the half period of the waveform. It's the time between two successive points in KY at the center of K-space. And so that's a metric that tells you how well you're doing. Typical head gradient, it's about half a millisecond. Typical body gradient's about half a millisecond. Head gradients can go a bit faster. For a 3 millimeter image, it changes with the resolution, because the high res you have to go farther out. So what happens to this voxel above the susceptibility area in EPI? Well, there's distortion from the phase accrual, and and there's also a shortening of T2 star because there's a distribution of T2 time constants across the voxel. So let's look at this. Here's 5 different spins from top to bottom in the voxel. They'll each be processing at a different frequency because they're in a different field, and so they will fan out. That's T2 star decay, sort of coherent from top to bottom. And if you just look at the EPI image as a function of echo time, you see that the longer you wait, the more fanning out occurs, and the more of this dropout happens. Because of course, when they're completely fanned out, there's no net signal, and the image is just black at that location. And you really see it opening up above the temporal lobe and above the orbital frontal sinus. So this would say just use a short TE. That's a great idea, but it also means you'll limit your bold signal in other parts of the brain. The dephasing also occurs across the slice, so a thinner slice gives less opportunity for a top-to-bottom phase difference. And so that's our number one way of dealing with this, is just to go with a thinner slice. As here you see the 3 millimeter slice is quite a bit better. It's kind of looping a little too fast. Here's a 1 millimeter slice, and you can almost get rid of the orbital frontal susceptibility with a 1 millimeter slice. Okay, shimming is one way to deal with it. Thinner slices has some drawbacks. You need more slices to cover the brain. Paying attention to slice orientation can also help. Shorter TE is good in that particular area, but it means you'll see less bold in the rest of the brain. It's just quick, I'm a little out of time. For the EPI, the susceptibility can give either a compression or an expansion in terms of distortion. That's just whether the local gradient is aligned with the blips or anti-aligned with the blips. It either stretches or compresses. This is a little toggle back and forth between a blip up and a blip down. Always useful to look at and a little bit scary. Here's a bunch of different echo spacings taken with a head gradient, showing that the faster this echo spacing is, the better, less distortion you'll have. And so our best method is better gradients. You can try to correct it. Multi-shot imaging has drawbacks from motion and physiological noise. Refocusing pulses could be used, but better gradients is probably the best one. And recently, parallel imaging has really come to save us. And I should add shimming. I'll just very quickly say that better shimming, I think, is just around the corner for us. A lot of groups are working at very high-order shimming with a number of different techniques. I think this is ours. I'm not going to go through it. It's built into the head coil, but I think it's a good possibility. The other thing we do is we leave out every other line, and that causes us to traverse K-space faster, and that's very helpful. I'm just going to skip the basic sense grappa stuff and go right to how it helps shimmy. I shouldn't have done that with a lot of clicks. Sorry about this. This is a sort of standard way of taking K-space, and the way I think about it with grappa is all the coils forming an encoding ball that when you take one sweep through K-space, you fill in multiple lines simultaneously, where the gradients, of course, create the basic line, but the coil combinations create the adjacent lines and create the width of that ball. If you accelerate too much, of course, you push the ability of the coils to unalias, and we see this noise enhancement becomes too significant. But it's very useful for getting rid of this distortion. Here's a high-res EPI without acceleration compared to with acceleration. Whoops. See if I can toggle back and forth. And you can really see how a factor of 4 acceleration cleans up that frontal lobe. And so with 1 millimeter isotropic, it tends to look pretty good even at these high resolutions. And this is, of course, our secret to getting these very high resolution 7T images. We seldom do anything but a factor of 4 acceleration. And this is where the coils have really come into play recently. So they're doing most of the encoding. And of course, if we want a 1 millimeter isotropic whole brain, and it's 120 slices, and it takes, take 10 seconds to take that, that slows down our time resolution. And so luckily, simultaneous multi-slice has stepped in, and now we can do these high-res whole brain acquisitions in a reasonable TR, say under 3 seconds. I'm just going to very briefly touch upon one last aliasing method. That's this wave-Kaipi method, which we've recently introduced, where we don't just take lines in K-space, but we take corkscrew trajectories. And that throws the aliasing everywhere. And so it's in the same genre of the blipped Kaipi, in that we want to spread out the aliasing to make the unaliasing problem easier to do. And it really effectively throws it in 3 directions and gets rid of it. So here's a 10-fold accelerated image. Would have taken about an hour to acquire without acceleration, and now it's about 5 minutes. And here's, impressively, an MP RAGE exam, 1 millimeter isotropic whole brain, 47 seconds. So these free surfer type exams, we used to average 2 9-minute acquisitions and run them through free surfer. It's a 47-second acquisition that's actually higher resolution than those old ones. And when I say 47 seconds, I include all the grappa pre-scan stuff as well. It's not cheating. So thank you very much. I've gone a little bit over time. Hopefully we'll have a few time for questions. If not, catch me afterwards.